Using our calibration method, we know how to estimate the projection matrix. Now, what's interesting is we can go one step further. We can take this projection matrix and actually decompose it into the intrinsic matrix, which has all the internal parameters, and the extrinsic matrix, which has the external parameters of the camera. So let's take a look at how that's done. Here you have your projection matrix P, which is what we've estimated using our calibration method. And we know that the projection matrix P is the product of the intrinsic matrix Mint and the extrinsic matrix Mxt. The intrinsic matrix has all the internal parameters, and the extrinsic matrix has the external parameters right here. Now let's consider this 3x3 submatrix of P. Remember, we know all of these elements. So that submatrix, that block, is the product of this 3x3 submatrix, which we defined earlier to be the calibration matrix K. It has the internal parameters. So it's a product of that with the rotation matrix R. And we know that the calibration matrix K is an upper right triangular matrix. These are non-zero elements, these are zero. And we also know that the rotation matrix is an orthonormal matrix. We discussed this earlier. And it turns out that if you have a matrix that is the product of an upper right triangular matrix and an orthonormal matrix, you can use a very powerful tool in linear algebra called QR factorization to compute the two matrices from their product. So in other words, from this 3x3 matrix, which is known to us, we can actually compute K and R. In other words, we can estimate all the internal parameters and the rotation matrix. Very powerful technique. And so now there's one piece missing here, which is we have found rotation, we have found the internal parameters, but we need to find the translation as well. Well, that's easy. What we can do is to look at the last column of P, which is this right here. Well, that happens to be equal to your calibration matrix K with the internal parameters times the translation vector right here. And we happen to know K already, and therefore we can find the translation vector as well, which is K inverse this column of P. And we're done. So this is interesting. We found the projection matrix. In this projection matrix, all the internal and external parameters were jumbled up. But we were able to, using techniques in linear algebra, tear apart the internal and external parameters of the camera from the projection matrix. Now, there's one thing that I should state here for the sake of completeness, which is there may be other intrinsic parameters which we haven't considered. In the case of pinholes, we essentially have taken care of all the factors that are at work. But when you talk about a lens, you could have additional aberrations of the type we discussed before. For instance, you may have radial distortion, where you have points being thrown out away from the center, or you may have tangential distortion, where you have twisting of points in the image. These tend to be nonlinear effects, and the way that you would actually take care of them or incorporate them is either throwing in more parameters into our model, our camera model, to accommodate for these distortions. But generally speaking, that makes the camera model nonlinear. Another way to do this is that you calibrate for these kinds of distortions a priori, separate that out, and then you have a linearized camera model, and then use that to perform the calibration that we just described.